of a cut we made it here is a directed cut in the graph between the source and a fixed data collector is a subset of edges, all is a subset of edges such that there is no directed path starting from S to DC that does not have one or more edges. So that means any directed path from source to data collector should have one or more edges in the cut, then only it is a cut. Okay. So, if you look at now this definition here, so we chosen this node and this node for data collector. So, then if you do not choose this and you only choose this is the cut, then there is a path from here to here that does not include this. So, hence for the cut to happen you need to have one of these and then you have two other ones you have to show that. So, obviously the cut has 1 plus 2 beta has to be greater than or equal to 2 MB, 2 megabyte, that is the size of the file, and so you get a bound. In any other way you do, it will be much smaller. For example, if you take 2 here, then it is already greater than 2, then it is not an optimal. So, this is that will not be a min cut, that can be a cut, but this will not be a min cut. So, this actually explains the kind of the bandwidth storage trade off that we are looking into. That is one thing that we discussed, that was nice, and the other one is basically this example. So, to actually understand this example a little bit more clearer. So, this is about a functional repair. So, in a function repair what happens is initially in a source node it creates some node, and then as and when nodes are failed, new nodes are created, but the new nodes have a ability to give ability to reconstruct satisfy the reconstruction property of the code such that any two of them should be able to reconstruct the data whatever is required. That is all the necessity thing. So, you are not really required to recreate it in the same way as it was before. So, under that model this was actually to show you, instead of actually downloading 2 files or 2 symbol worth, you can only send only 3 for that. And for that what it does is that just to understand further the linear combination of the information that was sent, that will be noted down as we pass through. So, for example, here when this was sent here 1 and 2, so this node will know, this will know that it is actually 1 plus 2 times B1. So, now you can see that this particular data is created by from 1 times this, 2 times this and 1 times this. So, if you can say that, you see it is 5A1. So, 4A1 plus 1 5A1, 5B1 plus 2B2 7B1 and 4A2 plus 2 times 4A2. So, 8A2 and 5B2 plus 5B2 times 6B2, no 5B2 times 7B2. So, this is 1 times 5B2, then another 2 times this. Okay. Is it clear? So, this one is 1 time, this is 2 times this and 1 times this, 4A1 plus, there is no A1 here, so that is 4A1 plus 1, for next 5B1 plus 2B1 7B1, correct, 8A2, so 4A2 twice of this A2, that is correct, there is no A2 there, then 7B2 5 plus 2B2, correct, that is correct, and same way this. So, you can see that this is a linear combination of the previous message, but that will be enough. Now, which code is that having this property? Is it easy to find? That is the question that the coders will do, but what the paper says is that if you have a large enough finite field and by choosing just the simply random linear communication, you can actually solve this problem. How does they do? So, they basically take it as a network theoretic problem. So, they say convert this problem into multicasting network, and in the multicasting network what is the condition? So, if there are n nodes, all n choose 2 failures it has to recognize. So, you put develop a information flow graph for that and show that it is always possible, okay, and from network theoretic things, okay. That is again existence results, but we have a better thing. I mean, we do not go through that kind of construction for the in this course, but that is how the functional repair is done. So, do you understand the difference between now functional repair and exact repair? Now, for the exact repair, coming up with a bandwidth storage trade off is a challenging question, and there are many work happening so far. So, for example, when you have a bandwidth trade off like this, the exact repair curve could be just above it. So, what this bandwidth trade off tells is that you could not have a solution underneath this curve, but everything is possible here, and the exact one, if it is exact repair, it is actually much above, okay. So, how much what is the thing is there are a lot of open questions. There is some developments happened, and some things, and for some certain length they have actually completely characterized, but for functional repair everything has been characterized. So far that is the state of affair for this regenerative code, okay. So, in order to, for example, and Aaron actually mentioned that now when you try to actually improve, implement this with this kind of code, now obviously these nodes have to be there in a network, and some of the things that we need to consider is the bandwidth, how much the delay that it has. Now, what kind of a codes optimize into that? It's a question that's not so easily solved, okay. Now, one of the things even in the paper by Demarkis, it mentions that if you have these nodes, I mean, if you know all this information, let us say bandwidth between different nodes, can you now place these nodes in an appropriate fashion, so that in case of a failure you will be able to recover with a minimal cost. So, can we formulate that? And as such, when networking is a very dynamic situation, so if these underlying communication links, the properties quite changes fast, how can we to adopt this? And so, these are all the things which will be for the future directions, and we will go through. So, we will go through some of those things. So, what type of codes are best for these things is there are still lots of open questions, but the idea of regenerative code actually throws up a new prospects of in decoding, where bandwidth is taken into account, unless in other erasure coding techniques it was mainly able to just recover from an error. That's probably the bandwidth was not a main thing in the past, because probably the drives were in the same computer, and so the rates were used to do that job. But now with the distributed storage, this come into focus, and there were lots of interesting applications, like Facebook come up with the 1410 Reed-Solomon code, and it's already there in the part of the Hadoop, and there are many efforts to actually improve this code. So, people have achieved from computer science and networking community to improve the performance by using lots of ad hoc and very those techniques, and some of them we will discuss. But again, can we now the developments happening in this area, can we apply it into the network and get some results? Those kind of things are still open. So, this is not very, we do not have a full say on those things. So, let us try to understand any other doubts in this thing. So, maybe we will go back into the situation. That is only to explain the idea and the bound. So, let us now we'll go to this idea, this of exact repair idea, and in this case now we probably with the course now we are having the first line, if you count something like it's like a like an RS code, whatever we discussed. And some other, if I add more lines like this and create like a vector code, it's more like an array code. I can still consider it from a coding theory perspective in that session, so we can all understand. But let's try to understand here the interference alignment. That was the thing. I think I was talking to a few people, so if you have doubts, and probably let's try to understand this very clearly, because I put up some of this example. From the there are many ways to do it, but let's look at it here. So idea is that now each node now has 2 symbols, right? Yeah, and if you do it in a naive erasure coding way, you need to download 4 symbols to repair it. But what we had to show in this case was just by using only 3 symbols, you can recover the node. Okay, so let's do x1, x2. So did you understand that? Do you have any questions in this? Like now I mentioned that if this node is obtained, for example, when you multiply 2 inverse here, okay, so 2 inverse of this one, what you get is 2 inverse times x1 plus y1. Then if you multiply 3 inverse here, 3 inverse then that gives you y2, so that is 3 inverse times 2 x2 plus y2. So with that, multiplying by those 2 vectors, like 2 inverse and 3 inverse to this, what I have done is I have isolated y1 y2, which is an interference for me to construct A2 from others. So I have done that. So then I get y1 y2 from here, and here there was already y1 y2 was aligned into this. So for example, this particular subspace is aligned into this, and now I have actually converted the subspace in here also into make it I1 y2. So now y1 plus y2, I can take it as a new variable, let us say some y dash, and all of them can be completely cancelled from each other because they are the same. So this is the idea of interference alignment. People did it for when a wireless communication, and when they were trying to get with some multiple antennas and how to align. How to align the interference from other antennas to improve the bandwidth there. So that idea now can be applied to here to recover it. So that way you can do. So this is one thing. But this closely, what I am saying is the idea is that is there any other way you could do? Can you please tell me? So if this is because the code is like this, right? I can treat to be so for example, let's do that for another way to do it is to assume that now we see the thing is, because it's a 4-2, if this node fails, then what else? Then I need to be able to get it from the others to do it. So I need, in that case, x1 plus y1 I need to create. So which one is the interference alignment? You have to think. So I want actually x1 y1 as that's what my desired one. So for this, all other things are interference. Okay. Pardon?
I also need x2 plus y2.
You also need x2 plus y2. Yes. So we need to actually now convert these linear equations. So this node, this node. So obviously you need to do some kind of things for here. So for example, here you can probably. So that's why does there exist a subspace? Because this is one of the parity nodes. It's a bit more challenging. Okay, can we take that as an exercise and do? But another thing what you can do is, what about this? If this is failed, then how will you do? That's not difficult. So that's why sometimes when people come up with codes for solutions for the information part of the code is easier, and for something for the parity codes is a bit not that so easier. So there are solutions in that way as well. But so is that clear now, this interference alignment? Yeah. So this is interference alignment. Then we also discussed about that, and so now idea is that field size to represent data. So if I now insist on for example, so as that if it is a functional repair, then the theory tells us that if you choose a large enough finite field, is very big enough, then by taking a random linear combination it's always possible to do, yeah, that kind of things. But large enough finite field is more expensive, right? We can't implement, as I told you yesterday with the RAID, and most of the time the companies are prefer to do only 8-bit or 16-bit or 32. They can't do many more things. So we need a solution that where the field size is quite low, small. So this is actually a kind of an interesting open problem. There are many people working on it. So when we look at some high rate code words which has some locality property, it is possible there are some results, but this in general finding the appropriate, what is the best size for the finite field is not so easy. Yeah. Because I gave one example, but when we try to do it, we should try to have a for let us say we have nkd, I want nk, I want, let us say, one of the things is one of the region is that if you have a k by n is less than half and k by n is greater than half. So when you have a low rate code, that means that it has lots of parity bits, and obviously you could see that there are lots of redundant information available in it, so which means that it's not efficient. So most of the MBR codes sometimes it comes under that category, but to have codes which has a high rate is still they're kind of interesting, and there are some class of codes which we will discuss in the course later that comes up, including our framework based codes. Okay. So those are the considerations. So you have a field size, and also then what happens is another thing, that is a let's say sub-packetization idea. So just as we do, so now we can have, every node can have now it can now symbol L symbols of over alpha. So the alpha will be L, and what should be the, because this is the sub packet, size of the sub packet, so number of symbols from that, how that should help us to give the thing. This is also another direction people are, and we looked at the regeneration idea with this code. So you probably go through the thing again, so if you have more questions on this, and we'll come back. And for the type of things like I said I asked you to prove lemma yesterday. Has anyone I saw one proof. Is there anybody proved? You proved? Okay, show it to me. And then probably we will discuss. But maybe I can, at this point I can also show simple idea of so if you have a series, what's the summation of this series? A minus 1. Okay. Now think of this, and also look. Of course, this is in numbers what I said, but you can also think a similar thing about polynomials. So most of the times when you took polynomials, you take x power n minus 1. Okay. Now this polynomial x power n minus 1, I have chosen deliberately alpha to be of order n. So you can also sometimes represent x power minus as 1 plus x up to x n minus 1 times 1 plus x, correct? So you can factorize x power n minus 1 into, yeah. So this is where some of these things I can actually do it with Magma. So you can learn a lot more about coding theory by just calling appropriate functions in this, and so it will give you idea about it, you know. So sometimes it's faster to study, especially finite fields. Let us take, you know, I will tell you F16 is equal to finite field of order 16. I can also make, for example, in this case, say x. Okay, so what is F16? It is a finite field of order 2. Okay, you can do like this. Then I can say, now other day I was thinking, you know, for I in F16 to, I would say just list and for. So it lists as a power of alpha. Okay, then you can say that element to sequence of for example x power 7, it will give you element to sequence. Okay, now I can also think, you know, sequence to element, because it assumes that it is in the same direct things, like, you know, let us say 1 1 1 1. What would you think it will be? It's probably asking for a bad argument times, because see in the earlier case when the element to sequence, it knew that you know, the what I need to do is the domain was very clear to Magma, and then it gave a sequence to do it, because Magma internally keeps the x, even though it is x power something, it keeps it as a polynomial or a sequence, so it can easily do. Whereas in the other thing, then it will like it want for example, I can probably try to cast try to see whether it works, but I may not have defined F2 yet. So F2 is not defined, so it says finite field 2. I can ask maybe F2 in F16. I can ask question, what should I get? True? Oh, it's again bad argument types. It probably can't compare, because when I created F16 I didn't use this directly, because Magma has some things, but I can check F16 is finite field of order 2, F16 is this. So if I need to, let us say, just for another argument sake, maybe I will say FA16 as a new thing. So maybe FA16 is a extension field of F2 of size 4. Maybe it will take, I mean, I am just going no, extension field is not defined, so I had to check. No references for, no, that is not correct. Extension field, yeah, it is there. So you see, extension field, I had to given a finite field phi and a literal identifier x, polynomial of p degree over the expression, so it will give you extension field. Okay, let me do that now. Extension field, I want to give it as F2 and F2 comma, say let us say make a literal element t just for argument's sake, and a polynomial t square plus t plus 1, no t4 plus t plus 1. I do not know whether it will accept, let me check. No, so it's a bad syntax, because the polynomial has not been defined, that is the thing. Yeah, so then I need to have a polynomial thing. So you know, polynomials can be defined this way. P of t can be equal to polynomial ring t polynomial ring t has not been declared, so you have to say F2. Now it's all univariate polynomial degree over that. Then I can now try extension field. This should work now. No, still not work. So, let us say, so given a finite field f, a literal identifier x, a polynomial p of degree n over f presented as x. Okay, so it should work, but I might have made f2 comma f. So, I can ask now, let us say, is irreducible, the polynomial is, oh, I did not have a polynomial, that is the problem, correct. Let us say P1 equal to T4 plus T plus 1. So, I can ask is irreducible P1 true. So, now I can go with extension field and I will go here P1. Oh.
T is not required
T is not required, but I want T. Oh, no, I made a mistake. No, yes, it is a different kind of thing. So, when you are doing this magma, I can't use the parenthesis. Yes, it now gives a finite field. Okay. So, now you can run over it and ask some questions, and you can find all the property, especially Reed-Solomon code, what you can construct yourself. Maybe let us check whether you have a RS code already built into this. Maybe no. No, maybe I have Matson, Solomon. Okay, Solomon. Reed-Solomon. Okay, Reed-Solomon code. Ah, yeah, it is there. See, Reed-Solomon code. It only just for, let us say, one Reed-Solomon for code of k comma d comma b. So, given a finite field, a positive integer d, return Reed-Solomon code of length n equal to q minus 1 and design distance d. This corresponds to BCH code. I mean, so this is another one, but let us see the second one. Just is a finite key, and you give a d, and second one gives a second one. Let me check the second one. What it does. Second one is basically given a positive integer n and such that q equal to n plus 1. Okay. Or if p, so again p is given as a non-negative integer, then the primitive element is first raised to bth power. So all the things the code he is giving is just exactly the one that we covered in the class. Yeah. But what gets used is basically a linear equation, which is some kind of truncated code over this, because we can't always have length one less than the previous. If we, in most of cases in our erasure code, our length will be not very big, 3, 7, 4, 8 like that. So those things you can use the linear algebra tools of the Magma, and you can do something. Okay. So now, given that clue, you try to prove the lemma there, and that will be pretty obvious. So the crucial point in that proof, I choose one of them, the g, the constant term of g is 0. So when you multiply by 2, so the constant term of the product will also have a 0, because you start with 0. So you take any polynomial, if you try to multiply without the constant term, that will not have so for example, you have whatever may be the polynomial, the moment you multiply by x, that the constant term of the product will go move once. That is actually used to in that one. So this is a simple result. Yeah. So let me know if you have. So I think the Magma you can use, and also especially on the linear code, even somebody noted me you worked on the syndrome table I have given it. There are errors were there at the end. So that's clearly, so you know how to do that, but syndrome can be checked here. There are some appropriate functions. You can define a code, and you can also get a syndrome table. That decoding also you can try on this.
Do we have some
Standard array decoding, huh?
some documentation for this?
Pardon?
Do we have some
Presentation?
documentation which has this interface?
So the thing is to be able to understand Magma. I have many of my computer science students, I find it very difficult to read, because their documentation is mainly for mathematicians. So if you think from a mathematically, it's easy to understand, but if it is trying to do, so for example, you can write a program involving the objects given there. So there's anyone heard of GAP, a software called GAP, GAP, for the group studying group. So this was built up based on that, and now this has come out to be very big. But yes, there are some information available. So if you go to Magma online, so I think this is a very good useful tool if you especially if you want to study something. So Magma, so this is the maths at University of Sydney. So here some documentation is there. So especially first steps in Magma, and you can solving problems with Magma. You get some help. You get it, but it will be a little bit. I mean, once you read couple of pages and you do, so then it will start making sense. Otherwise, it's a bit. It also has a function called casting. So for example, sometimes you can define something over integers and then you can cast as something else. So that time it shows whether the particular object can be can be translated or not. If not, it will give you some error and those kind of things. So like this is what you normally in programming languages you do. So you can go here, something has been updated, I can see, because looks different. So there is a lot of finite Magma solution how to do. So find solution. Actually, the simplest thing you could write to do is to actually find say inverse of a modulo n number by using the Magma gives the XGCD algorithm. Use the XGCD algorithm and write your own modulo n number. So then you will understand how to write a function. So if you want to write a function something here, I haven't done it for a while now, let me check. So here so you can say function, say inverse mod n, let us say that is the function, inverse mod n, and that takes as a comma n. So a comma n. So okay. Oh yeah. But I also need to give this, I think, function. I think this is the I can send some functions that I wrote on. I can't recall now the syntax for the function. Let me just go. Oh, so many things it will come. Magma mapping. So much of. I think or maybe it is that one. So inverse mod n equal to function a comma n. Let us say if it accepts, then yes. So now I am defining a function inverse mod n that is equal to function n. So I want to return the inverse of a mod n. Okay, what I should do? So let me just have a buffer. Let us call for g equal to say 1 just for things. Then what I do? So you have to actually you have to look at the function that what it returns, and then you should have a variable to receive that function. So yeah, can you somebody try and then come back? Maybe next another time we'll discuss. Yeah. So just write a function for xgn. You can also write your own Euclidean this function which I gave you in the other slides. Yeah. Yeah. So there is a theorem proving version of the extended GCD algorithm. You can write down and show, and using that you write your own function for the inverse modulo n. So that gives you a bit more experience in handling the multiplications and stuff, and then you can follow the especially the vector space and other ideas. Okay. So this is the kind of we do this idea. So if you have any other questions on this matter today. Pardon?
How will we decide whether we should go for an exact repair or a functional repair? How do they differ in fact? In both cases we can reconstruct and repair. Both could be done. Whether you are going for an exact repair or a functional repair, both data reconstruction and node repair could be done.
So what her question is whether when should we do functional repair, when should we do exact repair? I mean from the in this lecture we show these two as the two concept different thing, but now in a distributed storage how to go about it. I mean in practice many people would like to have an exact repair, because you wouldn't like when you have some node has failed and you don't want to have a equivalent version, right? You want to have a, so normally what is preferred is exact repair.
But functional repair performs better than exact repair.
We do have a solution. For example, there exists a regenerative code solution that actually that's satisfied in the functional repair, but it's not easy to say that the functional repair is better than the exact repair or not. But what is preferable is the exact repair from other consideration of a distributed storage. So when you sometimes distributed storage you most of the time the data is kept in the information node, so that there is not much of a coding is done. So we only have extra parity. So when we discuss the Hadoop Hadoop system, we will come to know. So you could some people have the hybrid model, that is the exact repair of the information nodes and other things may be possible, but I haven't seen any storage nodes that uses functional repair. So most of the things you will go with the exact repair. Yeah. Okay. Okay, so we will just look at write one or two Magma programs that will help you to get and so you can have some questions on it, then we can we can go over it, maybe construct a code and a Magma, and let us say have a linear code of certain length, find out its array decoding for that, syndromes decoding, standard array, you can construct standard array, all those functions are available on with Magma. So that way whatever abstract concepts that you see, it may be easier to handle. Okay, so maybe we will practice that and we'll continue. So at 3 o'clock today Adrish will continue on the information theory part. Okay.